Hi, thanks for joining the talk on critical spare parts management in maritime shipping, selection and control. This is a talk that was presented at the Hawaiian International Conference for System Sciences, 57th time, in the mini track Decision Analytics, Intelligent Decision Support for Logistics and Supply Chain Management. This includes, or the presentation is about a paper that I published together with two of my students, Matthias Patzke and Sabah Said. Yeah, let's look into the agenda. It should be a short talk, so I will shortly sketch the project and problem description. Then I will talk about the results that we achieved for spare parts classification, and then look into conclusions and further research. So this work is part of a project that is called ShippingLab, and it pertains to the work package 1.3, where we have two activity groups. The first one is aims at developing and validating a digital twin or models for engine fault detection and wear or failure prediction of main engines of ships. So the outcome should be the failure rate estimates of failure prediction, and this gives then the input to spare parts demand forecasting in amount and time, leading to the second group that occupies themselves with digitization and optimization of maintenance and spare parts logistics for the shipping industry or for a specific fleet. We had, because the project is finished, several shipping lines with us in the project that are listed here. So when it comes to spare parts logistics optimization for a fleet that is operating in tram shipping, so bulk shipping going like taxi driving from port A to port B or being called somewhere else, then we need to first determine, because our goal was to look into where to place buffer stocks of spare parts in an intelligent way, so they are available in the best way and at the best service level for the fleet that needs maintenance. So placing them in strategically clever places at a good amount, so that no ad hoc or express shippings that might be more expensive need to take place, or in the worst case that a ship will be idle because there is a major maintenance requirement or a breakdown and leading to a ship idleness. This is very expensive. So to do spare parts logistics optimization, we first need to look at the what. And that means that we need to determine and select a criterion that allows us to call a spare part critical for the operation of a ship. The when, and this is done by the group, by the second group within the project. The when should be ideally determined by the first group that looks into failure rate estimation and prediction, because then we can have the time to the estimated time of next failure of a certain part, and then have some more time to allocate the spare part to the best place where the ship will need maintenance operation or can pick it up, simply speaking. And then we need to determine, when we have that, how much and where we should allocate them. So we look here in this place at spare parts allocation of the overall network. And this is, in our case, with the shipping lines that we have, the world. We are aiming also in looking into pooling or sharing of inventory contracts for different shipping lines, because if they collaborate together and they have similar ship types, then spare parts can be exchanged. And that also then decreases the overall costs of providing spare parts for all the partners. So one item or one focus point was also to look into that. And then looking into supplier selection based on timing and costs. So cost is also an issue, of course. One aspect of this project was the out of use or dry dock cost estimation. So dry dock is when the ship needs to go into a dry dock for major overhauling That means that there is idle time of the ship where it cannot operate, but also to look into the cost for in-use cost estimation. So you need to imagine that while the ship is sailing and bringing cargo from A to B, maintenance continuously takes place. So this is in-use maintenance. So the problem setting, solution method, and challenges that we have focused is the following. This is an overall ship. So it contains a ship hull. We have propeller and main engine, specific ship equipment, navigation communication equipment, radar and searchlights, other electronic components, and crew-specific equipment. And with our project, we focused on the propeller and the main engine. So mainly about the main engine, which is displayed here. So you might think, wow, this looks quite complex, but somehow manageable. So what we need to find out when we look into this main engine is we need to define and measure to classify the criticality of the spare parts. And that is what we've done through an ABC, a classical ABC analysis. So here the criticality, where we had several options to define that. That is the volume, the price, the lead time of reordering a certain spare part, or the consequences of missing items. And this is generally speaking. So these are the measures that we find in the literature. And then we can analyze the consumption pattern using demand variation classification by a classical XYZ analysis. And this is what we have also done. So if we look now into our case study that we have applied, we use here for this paper a single case study. So we looked only in one of the data sets that had the best data quality. We look into a time horizon of 5 years, because then we could also capture the dry dock of a ship that normally needs to go through several maintenance cycles. And we got the consumption data from a company from their planned maintenance system. And this system includes the maintenance task schedules and then also the spare parts usage. So we could get an idea of what has been used from that side. We look into 9 ships that have the same ship type or that are from the same type, because then they are comparable. And we look into purchasing data. So we had quite a data set with 1,179 rows and 22 columns, so 22 features, as we call it in data science. After filtering for the main engine, we had 425 items left. And we also had from information the noon report, so the position of the ship at noon. Yeah. Challenges that we faced throughout the process were the following. So as I mentioned, we looked into bulk shipping. So we tried that out, but a position prediction was absolute impossible. As I said, bulk shipping is like taxi driving. And based on the historic data that we had, we tried to estimate where the ship would go next, but this did not work out. Another challenge was the data quality and availability. This is why we focused only on one case study, because the quality of other data sets was not good enough, so we could work with it. And also the data quality of the data set we worked with was quite challenging, but nevertheless, we found some nice results from it. What we see, and this is in general, not just for our case study, is that maritime spare parts have lumpy or intermittent demand patterns. And this makes forecasting of the demand quite demanding or difficult, because you can have times, or you can have an order of a certain item at 1 year, maybe once, demanding 10 items, and then 2 years, nothing. And then you might have the order of 1. So the statistical methods that we have for demand forecasting are not working in that case. So we need specific algorithms that are in place, but they are difficult to handle, but we have research available for that. And also a challenge was the complexity of the main engine. So actually determining which are the critical spare parts is quite a difficult endeavor, because you have seen already that we have certain criteria to apply available, but such an engine is so complex that it's we talk to the experts and they say also, well, you can have a simple O-ring that if that one is scrapped or does not work properly, the whole engine gets problems. So it's the cause and effects of certain spare parts can be critical, but it's difficult to estimate what will happen if it doesn't work, if I explain myself correctly. So yeah, so it's difficult to determine which parts are actually critical, because also a simple O-ring, if it's missing, can be critical. So everything just needs to fit for such a complex engine. Yeah, and well, I was impressed by this picture because you see that such a main engine of a ship can be huge. So you see here the operation, the maintenance crew, and the operations of this of the ship standing on actually the main engine. Yeah. So what we learned from the literature when we skimmed it through is we looked into the ABC-XYZ classification system to make a wise and informed selection of the criticality criterion for the ABC component of the categorization, looking into class limits for the categorization, and looking also at the time horizon. And that, how we pick it, also for the demand estimation, depends on the industry. So we can have fast-moving items where it's good to do the classification in a weekly period, or if they are not moving too much in a monthly, or in our case, more on a yearly basis or on a multiple yearly basis. What should be done, and this is always the case, of course, for data science project, is to perform outlier detection prior of doing the ABC-XYZ classification, because every outlier can distort, of course, the classification, as we are also working with averages. Yeah, and we looked also into the literature with respect to inventory control strategies for the different classes. But it was not conclusive what we found in the literature when it comes to inventory control, but also to allocation and reordering of spare parts. So we did some lead time analysis for the different items that we found. And here on the x-axis, we have this 426 items that pertain to the main engine. And then we measured we calculated the minimum versus maximum lead time per item number that occurred. And here on the y-axis, you see this difference in delays. So what we could see from this analysis was that the order behavior was influenced by the maintenance officers and plane maintenance strategy. That we have great differences in minimum and maximum lead time. So you see here, and this is covered by my picture, that the red line displays the minimum lead time that we encountered in orderings, and then the blue line is the maximum of the order lead time. And then we have also the numbers of the number of orders per item displayed at the bulks of the graphic. So you see here that we sorted these differences in lead time by the item. So this is why we have a descending order. So we have items with a huge difference, and then also items that have a low difference. But we can see that there's a great difference in minimum, maximum lead times. And sometimes this is also due to the data quality. So we encountered or we saw that we have negative lead times given in the data set, and we should perform outlier detection. So this needs to be said. We calculated the lead time by looking into the order placement date and the order delivery date, and then took the difference from that and then defining this as a lead time. This needs to be said. Yeah. So then we performed the ABC analysis, and this is one chart. So we defined the limits and we defined then the classes. So you can see here the table. Class RA has 80% share in the cost of items, and here we have 20% of the items accumulated to this. This is the classical ABC analysis that you will see also in industries like for manufacturing. So this amounts in class A, we find 42 of our items. And then we have the B class where we have actually 49 different items allocated to it. And their share in this class is roughly 10%. Share in costs, I need to say, and the share of items itself is 20%. So that is quite comparable to A, a little bit more actually. And the cumulative share in costs is 90% together with the A parts. And then in C, and this is interesting, we have most of the items allocated. So we have here 334 different item types allocated to that class. So these are parts that are really cheap, but I will come to this in a second. And this pertains nearly to 60% of our items in total from the 426 items that we have allocated to the main engine. So this is interesting, but not surprising. And then for the XYZ analysis, we have taken the coefficient of variation. This is defined by the sample standard deviation divided by the mean of each item. And here we see that outlier detection is important because we draw the sample mean for each item. So this can be distorted by outliers. And then you see the following picture. So we have, and now we need the definition in the X class. We have a count of 60% or more than 60% of items in class. And the X class is the one that has the lowest variation. And then we go to the Y class. This contains then 130 items in the class, so 30%. And then in the, so we can say that if we look into the items, there is, most of the items don't have a huge variation in their coefficient, or don't have a high coefficient of variation in the demand, which is interesting. And then we have those items who have a huge difference in demand. And here we find 30 items, so 7% of the overall items that we have. And here, I said it wrongly, we should have 425 items in total, not 26. Or I'm missing one item. Yeah. And this is the picture that you will get when you do an ABC XYZ analysis. And here I want to draw the attention to the demands that have the lowest coefficient of variation, where we find roughly 60% of all items. And we were able to see that we have a lot of items, actually 228 out of the 425, that are only ordered once in a time horizon of 5 years. So this is quite astonishing. These are items that rarely move or rarely go bad or rarely exchange, but they are ordered once in a good amount so that then they can sit for 5 years. So here we have tried to also give an idea about the inventory control strategy. So we see for the A items these are the ones that have a high value of the total costs of the parts. So they are the ones that we need to keep under control, or at least order just in time, because otherwise we would have it in the inventory or in the warehouse, and this binds a lot of financial resources. So normally you don't want to order them and then store them. So here we have 8 spare parts that pertain to that class, and they have a 75% of average share of the average total value of the overall spare parts. So this is quite a lot. And a 0 coefficient of variation, because they were ordered once. And here we would recommend a just-in-time supply for such items. If we look into the B items, for the X class, then we find here 21% of spare parts with 0.2% of average share of total value. So they are the medium expensive spare parts. And here we would say the coefficient of variation was more than 0, but not very much. So also here we would recommend a just-in-time supply or periodic inspection. And now if we look into the C parts, and they are interesting, really interesting, because here we find 236 of our spare parts allocated to it, with quite a very low coefficient of variation of the demand quality, and a very low average share of the total cost. So here we would say that periodic inspection of such a part is enough. We can also have a look at some other categories. So we might be interested in what happens for those items that have a very high value in terms of total costs and a very high demand variation. So in this category, this is the red part in the left low corner. We have 9 spare parts allocated to it with a 0.87 coefficient of demand quantity variation. So here we would recommend to, because it's varying, so we don't know when it would be needed, that we keep a low stock somewhere in a good allocation, or we need to keep close contact to the maintenance operators, or have good input from the failure rate estimation group, how likely it is for such a part to be needed for maintenance. So these are critical items that we should keep under control. Yeah, and I think that is for the moment everything that is interesting on this slide. So if we move on. Yeah, here I gave some more details on here, for instance, the A class. So maybe this is interesting. We find for the AX class very expensive items ranging from $880 to $13,000. And in this class, we have over 50% of item ordered that are ordered only once or up to 5 times in one unit. So I think for this AX class, it was that they are ordered only once. This is why they have a coefficient of variation of 0. If we look into the AY parts, we have there a wide range of expensive and inexpensive items. So items that have a price of $15 but up to 1,600. So that is quite a difference. And we have items, they are ordered often in quantities ranging from 10 up to 300 and more, like a ceiling ring that has been ordered 14 times in quantities from 10 to 50. So this is very difficult then to give a good inventory control strategy for such varying classes. So you see that this is a simple way of classifying spare parts, but it comes with difficulties. But at least it's better than having no classification. And then if we look into these parts, the 9 parts that I mentioned latest, we have here a wide range of expensive and inexpensive items, actually. So I was a little bit lying when I said these are mostly very expensive. But this is when we work with averages, which is always difficult because here we can have items with a price of $67 but up to 4,000. So this is quite a wide range. And they might be ordered 2 up to 17 times with quantities ranging from 9 items to 347. So also here it's quite a wide range. Yeah, and then I have the C parts because the B parts are not that interesting. And here I want once again to draw the attention to the CX parts, where we have 236 spare parts or item types. And here we see that 3 items out of 236 are ordered more than once. And that was a spring or a compressor right hand, a slide bearing or Viton O-ring. You don't have to know what that actually is. That are contributing to the coefficient of variation and then ranging from a value of prices from 20 pennies up to 1,030 US. That was true for a fuel pump hosing, complete with plunger and barrel and a suction valve and a sealing ring. As once again, you don't have to know what that actually is, but you are welcome to look that up, of course. Yeah. Good. So conclusions. What have we learned from our analysis? Well, we have learned that the ABCXYZ categorization is a very simple method, fairly easy to be applied for data sets in maritime spare parts management. We have done some validation with experts confirming the accuracy of the method. And actually, this company applies the method, which is nice, in order to define the criticality of the spare parts. So the next question is, and I have not yet spoken really about it, we have items that are required by IMO to be kept on board. So a good question is to look at how they are reordered by the case company. They are included also in our data set, but it would be interesting to look at them specifically. And then we need to dig deeper into the data. So we would like to find out which supplier delivered where, with which lead time certain items, where were the items delivered to mostly, and how costly was that. And further research then will be in applying more sophisticated machine learning algorithms for the item categorization to find out if that changes or if we have better classifications that can provide better inventory control strategies. And then we would also like to, now we were just using the ordering data from the company, but we would like to merge actually inventory control together with, that looks into procurement together with the maintenance perspectives. And I have provided one slide where we have already a nice visualization of this. And then also further research will investigate a criterion that is called consequences of missing items. But this is very complex to gather the data for it. So this is a very further research direction that we are aiming at. So here, and I think this is quite interesting, students of mine made a visualization where they depicted on the x-axis the date time here in years, and on the y-axis the number of items. And then we have these 3 lines with the item delivery dates, the item usage date, and then the difference in them, which is the item availability. And of course, this is in the middle of both. And this picture is even better because here it is enriched by, so we still have the item delivery, we have the order lead time. So when the spare part was delivered, and we see that there's a difference in between the order lead time and the item delivery time. I think that is the difference in between when the item was delivered and when it was used. So there we have then the item availability in the green line, or the item availability, which is the difference in the quantity of items delivered, of course, and the ones used. And here students made a suggestion for the minimum amount of items that should be held. And you see in the green corridor that this is a kind of an optimal amount of the items. And when the items drop below a certain minimum amount of items, then we can see that also together with the planned maintenance and item usage that we have seen, that there we get into the dangerous zone of maybe missing spare parts when they need to be scheduled or needed for maintenance. So I think this is a very nice chart that allows for a very good control of spare parts and look ahead. Of course, this is based now on historical data. So if we apply machine learning for doing estimates, then this can be enriched in looking into the future and giving very good planning data for maintenance and for purchasing certain items. One thing is, of course, that this is now done for one item number, which is a quite cheap O-ring that we display here. So one task will also be how to find a good way to aggregate the view or select the most critical parts. And this is once again pertaining to the difficulty in estimate or in determining which is the real criticality of items for the main engine. And then to see how we can aggregate this all so that we get an alert system when the purchasing department needs to order anew. Good. Thanks a lot for your attention. And yeah, thanks for listening in.